This video is about evaluating trigonometric expressions. As always, begin by reading through the textbook and taking some good notes, but now consider the following highlights for this topic. Let's begin by recalling several important things. First of all, in a previous topic, we've already established the trigonometric ratios summarized by the acronym SOHCAHTOA. You may recall this. This is from right triangle trigonometry. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So we, again, have already established that. We're going to bring that in as needed. Secondly, we've also already reviewed or established the addition and subtraction formulas. And we have actually 6 of these. So to recall, for example, sine of s plus t is equal to sine of s cosine of t plus cosine of s sine of t, and so on. We have the sum and subtraction, or addition and subtraction formulas for sine, cosine, and tangent, again established in previous topics. We're going to bring these in as needed. And now we're going to put these known facts together to evaluate these given expressions. Let's begin by looking at an example of what we're talking about here. Our first one begins as this: write, and then here's the expression given. It's the sine of, the input for the sine function is tangent inverse of x minus tangent inverse of y. Okay, so to say that quickly, it's the sine of tangent inverse of x minus tangent inverse of y. And that's all in the input for this sine function, but we want to write that in terms of x and y only. So you can see an x and a y in this expression, but you also have these tangent inverse functions floating around. We want to get rid of those and write it only in terms of x and y. So to do this, I'm going to make an organizational suggestion. This is just really a strategy to stay organized. I think it's helpful. And that is, we're going to take the expression inside the sine function, so our inputs here, which involve the two inverse tangent functions, and we're going to give those some simpler names. So for the first expression inside, we had tangent inverse of x. We're just going to call that by a new name that's only one letter, and in keeping with the convention of trigonometry, we'll use some Greek letters here. So we'll call that first expression theta. In other words, I'm going to substitute the simpler letter theta in for tangent inverse of x. But of course, we're going to do the exact same thing for the second expression, but give it its own name. So for the second expression, which was given as tangent inverse of y, we'll call that by its own simple single letter, and we'll stick to the Greek alphabet and use the letter phi. Again, another letter commonly used in trig. It looks like a, if you're not familiar, the letter phi looks like a 0 or an O, but with a vertical slash through it, as opposed to theta, which looks like an O with a horizontal slash through it. And so we'll just give that second expression, tangent inverse of y, its own letter, phi. And this will help us, I think, write things out in a simpler form. And I'll even color coordinate this so that we can separate these in our minds. And we'll also begin by recognizing that we're actually looking at a subtraction inside the sine input, which means this actually fits some of our previously known identities. As we said, we'll have to recall them. So let's do that right here before we get going. We're going to recall that the sine of, I believe the way we wrote it was s minus t in a previous topic. This is one of our formulas or identities that we hopefully have memorized by now, and it's going to come in handy here. So remember, sine surrounds, and it has the same sign, sign, as we've discussed. So that means we're going to say that sine of s minus t is really the sine of s times the cosine of t minus the cosine of s times the sine of t. So this identity will help us understand the one we're working with in this problem, because it's actually the sign of a subtraction, which is what the formula we just recalled will help us unpack. So as you can see, recalling things really does help organize and set it up. So let's do this, in fact, now with our new variables that we're going to use to substitute and make this simpler. So we'll rewrite our given expression as the sine of theta. Remember, that was the first letter we used to substitute for the first expression. So we have the sine of theta minus phi is the way that we've kind of written these substitutions in. And if we simply plug those new variables in with our subtraction identity that we just recalled, what we can say is that the sine of theta minus phi equals the sine of theta times the cosine of phi minus the cosine of theta times the sine of phi. And again, that's just keeping with the identity or the formula for the subtraction formula for sine that we just recalled. Now remember, our goal is to express all of this in terms of x and y only, and we're not there yet. In fact, we've kind of lost track of our x's and y's with this substitution. So what we're going to do now is unpack these substituted variables a little more. So if I'm going to say that theta, that is the variable we've let represent tangent inverse of x, that was just from the original expression given, right? That's what we let theta equal. I'm going to write this out here. Theta equals tangent inverse of x. If that's the case, we can do some trig operations that we know already, such as what if we just take the tangent of both sides of this? That would mean we have tangent of theta on the left side equals, well, just x on the right side, because tangent of tangent inverse would then cancel, right? So if we do this kind of simplification, we end up with something we can actually use in right triangle trigonometry. We have now tangent theta equals x. Now you could think of that as x over 1 if you want to force it into a ratio. And that might actually help, because if we then draw a right triangle, and remember our TOA for SOHCAHTOA, tangent is opposite over adjacent, then what we can do is label our theta in one of the acute angles of a right triangle. And if we have opposite over adjacent given as x over 1, now that we forced the ratio in on this, then we could say the opposite from theta across from it would be x, and the adjacent right next to it would be the side 1. Now, if we set up our right triangle that way, it works for our ratio, tangent theta equals x over 1, opposite over adjacent. And furthermore, we might be able to utilize this for the rest of what we need to fill in for our big old subtraction formula above, which involves cosines and sines, right, of this angle theta. So what we'll do or need is the third side of this right triangle we've now put into play. And to do that, we're going to have to use a little Pythagorean theorem. So we could say, for instance, x squared plus 1 squared equals, let's see, the hypotenuse I'll just call w for a second, w squared, to give it a name. And if that's the case, we could say w equals the square root. Yes, it'd be plus or minus, but we're only using the positive version for a hypotenuse. So we'll just use the plus. If I take the square root of both sides, of course, we'll have the square root of 1 plus x squared as our hypotenuse, which I've just conveniently given the letter w for the time being here. In fact, I'm going to replace that now. So we'll say that that hypotenuse w is really just the square root of 1 plus x squared. Now, with that side labeled of our right triangle, of course, we can fill in any ratio we need. And what we need in our expression we're trying to simplify here is sine theta and eventually cosine theta. So let's figure this out here using our trig ratios. Sine theta, using our SOHCAHTOA ratio, sine is opposite over hypotenuse, so that'd be x as the opposite over the hypotenuse, which we've just now found as the square root of 1 plus x squared. And similarly, now while we're at it, we could say the cosine of theta, again just using SOHCAHTOA ratios here, cosine would be adjacent, which is 1 over hypotenuse, which is the square root of 1 plus x squared. So now we have expressions in terms of, notice, only x that we can plug in for part of what we need. So if we go back up, let's do this kind of while we're at it here, back up to our expression that we're trying to simplify. For sine theta, we're simply going to replace that with what we just said sine theta is, which is x over the square root of 1 plus x squared. Now we still have cosine theta, cosine phi, which is next in our formula here to figure out. We'll get there. But then we also have, in the first factor of the second term, cosine theta. We know what that is by now. Cosine theta is 1 over the square root of 1 plus x squared. And again, we're not done because we have more to evaluate. We have to figure out now what cosine phi is and sine of phi. So in fact, let's make this our second effort here. If I make another equation that says phi equals what we had set it equal to, which at the beginning was our tangent inverse of y, just coming back to the original substitution there. Then if we take the tangent of both sides here, just like we did before, we'll have tangent of phi equals y. Now, just like we did previous with tangent of theta, we're going to put this as tangent phi equals y over 1. We'll force a ratio into it because that's actually helpful for us to set up a right triangle and use our right triangle trigonometry. So we'll do that. We'll draw a right triangle. We'll put our angle phi in one of the acute angle corners. And since tangent is opposite over adjacent, again coming from SOHCAHTOA, then we know the opposite of phi across from it would be the letter y this time, and the adjacent right next to it will be the number 1, the other leg of the triangle there. And then what we'll have to do is figure out the hypotenuse. Now we kind of already went through this in the previous step when doing tangent theta. The math of this one will be no different, except we're using the letter y now. So we could then just kind of borrow the idea and say, well, the hypotenuse is going to come out to be square root of 1 plus y squared, kind of like for the other previous triangle, it was square root of 1 plus x squared. Now having a right triangle fully labeled, we can go back up and remember what we're even trying to do. Remember, in our original expression here, we're trying to replace cosine of phi and sine of phi with some expressions that have x and or y in them. So cosine of phi and sine of phi is what we want in this phi right triangle. So we'll just put those in. Cosine of phi, given that cosine is adjacent over hypotenuse using SOHCAHTOA, cosine is adjacent, which is 1 over hypotenuse, which is the square root of 1 plus y squared. That again coming directly from this right triangle we now have. And so we needed cosine, and we have that now. We also need sine of phi. We'll put that in. So sine of phi in the same kind of way, using SOHCAHTOA. Sine is opposite, which is y, over hypotenuse, which is the square root of 1 plus y squared. And now we have expressions we can plug in above. So let's go up and do exactly that. I'm going to go back to my, expression above where we were plugging in one piece at a time. For cosine phi, what we just discussed is that it's really 1 over the square root of 1 plus y squared. We'll plug that in, 1 over the square root of 1 plus y squared. That's the second factor in our first term of the sine expansion for the subtraction formula there. And then the last term on the end would be sine of phi. We just figured out that's actually y over 1 square root of 1 plus y squared. We'll plug that in, y over the square root of 1 plus y squared. And what we're looking at now, notice, is fairly ugly, but it is an expression only in terms of x and y. So that means we can write probably one more step to get our answer. Notice that there's actually two terms here. If you think of this, let me highlight these here. We have the first term and the second term really coming from this subtraction formula for sine. And those are each fractions, but they would have the same denominator given what we've written and plugged in, because they both have the product of the square root of 1 plus x squared and square root of 1 plus y squared. Meaning, really, that's our common denominator we could use to write our final answer as one fraction. So we'll have the common denominator of square root of 1 plus x squared times the square root of 1 plus y squared, again coming directly from the previous step. And then the numerator would just be the subtraction we have. That's x times 1 for the first term, or x, and then a minus, and then a y times 1 for the second term, or in other words, y. So what we have is an expression only in terms of x and y, excuse me, for our final result. That final answer being a large fraction whose numerator is x minus y and whose denominator is the square root of 1 plus x squared times the square root of 1 plus y squared. Okay, let's move on and try another example. Our second example reads as follows. Evaluate the expression under the given conditions. Now the expression given is sine of theta plus phi. And then the conditions given for it are sine theta equals 5 over 13. Theta is in quadrant 1. Cosine phi is the fraction negative 2 square root of 5 over 5. And phi is in quadrant 2. Now, I think, again, like we did previously, it's going to help to draw some separate diagrams or approaches here, because we have two different variables going on. We know that theta is in quadrant 1. Now, in order to unpack the expression that we're trying to evaluate ultimately, which is this sine of theta plus phi, let's recall that that's actually a sum or addition identity for sine. So we're going to need this, and let's recall it because we have this formula from before. We can say that given the letters we're using here or given in this problem, we'll say it this way: sine of theta plus phi is equal to, and here's our identity. Remember, sine surrounds, and we're using the same sine SIGN for this. So we have sine of theta cosine of phi plus cosine of theta sine of phi. That's just using our identity from previous topic. But then, kind of like the previous example, I think it's helpful to color coordinate here and separate some things. We have two variables. We have this theta, and then we also have phi. And in order to get at what we're given here, which is the sine of theta and the cosine of phi, which they tell us in the expression and the quadrant, we're going to need a couple different diagrams to do this. So I think we'll probably do well to split these up, and let me focus on the fact that theta is in quadrant 1 and draw a diagram for that. So we'll just draw an xy axis diagram, coordinate plane. And we're going to draw a central angle triangle in quadrant 1, a right triangle, where the angle theta is the central angle at the origin. And the triangle's in quadrant 1 simply because that's what they told us it was, right? Theta is in quadrant 1. So we'll draw it that way. And furthermore, we know that the sine theta is 5 over 13. Well, if sine is opposite over hypotenuse, then we can label those sides as needed. 5 for the opposite side of sine, and then 13 for the hypotenuse of that right triangle that we've now drawn in quadrant 1. Now, where we're going with this in terms of theta is that we're going to have to understand what sine theta is. Well, we already know that, but we're also going to have to figure out what cosine theta is, because that's part of our expression. Notice then, if we're using this theta diagram, cosine would be adjacent over hypotenuse, but we don't know the adjacent side yet. So we'll give that a name. We'll just call it W to give it something different. And we got to figure out what that expression is, but thankfully that's just Pythagorean theorem. So we can say W squared plus 5 squared those are the squares of the two legs of our right triangle, must equal hypotenuse squared, which is 13 squared from what we've already known. This tells us that w squared equals 13 squared is 169, 25, or 5 squared is 25, so that should be 144 if we subtract 25 from 169, which means w is the square root of 144, which means w is 12. So we can replace w with 12 in our diagram, and that will give us plenty to use, because now we can say we already know sine theta, that was actually given to us. But now we know that cosine theta, which is adjacent over hypotenuse, would be 12 over 13. And now we can plug that in as needed in our expression. So as you can tell, we're kind of just piecing this together one part at a time. I'm now going to move on to phi. They told us that phi is in quadrant 2. So let's move down here and draw another diagram, a separate diagram for phi. It's just helpful to keep them separate, I think, rather than forcing them to both angles in one diagram. You probably could get away with it if you're careful, but I just recommend being extra careful and keep things separate. If phi is in quadrant 2, then just like we did for the first diagram, we're going to draw a triangle, but this time in quadrant 2. So the upper left region, still a right triangle, central angle, but now it's phi, our central angle. And so that's where phi is in quadrant 2. And we're also told that the cosine of phi is negative 2 root 5 over 5. Now, what's going on with the negative is a fair question, right? Well, remember, this is in quadrant 2. And so if cosine is adjacent over hypotenuse, then we have an adjacent side to fill in and a hypotenuse side to fill in. But remember, hypotenuse can always be positive because it's just simply a distance. Whereas the legs of a right triangle in a coordinate plane could have these signs of positive or negative depending on the direction. And in this case, since we're using a negative value for cosine, we'll leave the hypotenuse positive, but the x-coordinate or the x-coordinate leg, the x-direction leg of this right triangle, we'll make that the negative one. So if cosine is adjacent, we'll make then the lower leg of this triangle negative 2 root 5. There's our adjacent side. Over the hypotenuse, which is just given as 5, we'll make that positive. Now, if that's the case, remember, we need to figure out eventually what the cosine and the sine of phi are. We were given the cosine of phi already, but we have to figure out what the sine of phi is, which means we're going to have to know this opposite side of this new right triangle diagram. Well, you guessed it. Let's do what we just did last time. Give it a name. We'll use w, and then do the Pythagorean theorem. So we can say w squared plus negative 2 root 5 squared. Remember, that's the other leg of this triangle. So the squares of those legs added up will be the square of the hypotenuse, which of course, given as 5, would be 5 squared. So let's now simplify and solve for w here. We have w squared plus, if I'm squaring, here comes some algebra, if I'm squaring a radical expression that's negative, first of all, it's going to be positive. And secondly, we can square both the number 2 and the root 5. If you recall some root properties from algebra, this will become then 4 times 5, right? You're squaring the negative 2 to get a positive 4, and you're squaring the square root of 5 to get 5. So what we have here is w squared plus 4 times 5 equals 5 squared, which is 25. And now we're ready to simplify. This means w squared equals, if I do 4 times 5 as 20, but then subtract that from both sides, we get w squared equals 5. And then if we take the square root of that, we'll get w equals, now you could say it's technically plus or minus the square root of 5, because remember, side lengths of the legs on a right triangle like this could be positive or negative. However, in quadrant 2, this w is representing this vertical side length, so it's going to have to be the positive version of that. So I'm going to just note, you have plus or minus, but in this case, because of which quadrant we're in, it's positive. So I'll just kind of note that's because we're in quadrant 2. Okay, so now we have a value for w that we can use to plug in. We're ultimately trying to find the sine of phi. So if sine of phi, sine is always opposite over hypotenuse. Now we know the opposite side of this angle phi, previously labeled w, is the square root of 5, positive square root of 5. So sine of phi is opposite, which is square root of 5, over hypotenuse, which is 5. All right, let's go back to the ranch and plug in what we have now, which is quite a bit. So I'm going to go back to the original expression we're trying to evaluate here and substitute what we know. What we found is that sine of theta was actually given to us. That was the 5 over 13 as given. We'll plug that in place. The cosine of phi, that was also given to us. We'll plug that in as negative 2 root 5 over 5. Okay, then we have plus. Then we had to find some things. So cosine theta, we found that to be 12 over 13 from our first step. And then sine of phi, in a similar kind of step, we found to be square root of 5 over 5. If we then just do some of the arithmetic involved with this expression, we really have two terms and their fractions being multiplied. So across the top of the first fractions, you'll multiply simply 5 times negative 2 root 5. That would give us negative 10 root 5. And that's all over 13 times 5, which is 65. And then plus our next term would be, if you multiply across the numerators, 12 times root 5, so 12 square root of 5, and then down below it's 13 times 5 as well, which is also 65. So we're noticing a common denominator in place, which makes our lives easier. And on top, we're noticing like radicals, which means we can actually combine those. So this is just 12 root 5 minus 10 root 5. They have the same root, so it's like 12 minus 10, which is 2 root 5. And that's all over the common denominator of 65. And since we can't reduce that fraction any further, we're done there.